The effective number of bits, or ENOB, of an A to D converter is a lot like Bailey's beads. Now you might ask, what are Bailey's beads? During an eclipse, you see Bailey's beads as a spray of rainbow colors at the moment the sun starts to peek out around the moon. When you see this happen, you're not seeing the entire picture. There's much more behind the sighting of these beads as the sun is momentarily just not seen. The rainbow colors come from the different refractions of light rays in our Earth's atmosphere. It's like an optical prism. We sometimes think of ENOBs as a precise or accurate description of an ADC converter, but in fact, like Bailey's beads, is a general description, and it only describes part of the converter, and in particular, the converter's noise and distortion. My name is Bonnie Baker, and I am a senior engineer, applications engineer with Texas Instruments, and we're going to talk about the effective number of bits of A to D converters. There are two methods that are used to determine ENOB for an ADC. One is with an AC input signal, and the second is done using a DC input signal. When you have an AC input signal, the digital output is an FFT plot. It shows a fundamental input signal along with noise and distortion of the converter. We derive the effective number of bits from the converter's noise and distortion. This ENOB measurement is used for higher speed converters, which you would see with a pipeline or a SAR converter. When you have a DC input signal, a histogram of the data shows the average DC value of the input signal and the noise of the conversion. In this case, you derive ENOB measurements from the standard deviation or RMS value of the output data. As we go forward, be aware of the ENOB pitfalls. ENOB is only a figure of merit. It does not describe the operation of the entire converter over ranges of sampling frequencies and power supplies. Additionally, you're going to find that it excludes DC specifications such as offset and gain error. The linearity error of a converter is buried within the distortion specification, and missing codes are manifested in the converter noise. For AC input signals, ENOB or SINAD is one of the critical specifications for applications like digital oscilloscope, video, or wideband digital receivers. If you're testing an AC input, IEEE 1241 and some manufacturers use ENOB numbers to partially describe the ADC's performance. In the AC environment, we calculate ENOB from the converter's SINAD, which is the same as total harmonic distortion plus noise, or signal-to-noise ratio plus distortion. Now, SINAD is the calculated combination of the converter's signal-to-noise ratio, or SNR, and total harmonic distortion, or THD. In this simple formula for ENOB, 6.02 is a multiplier of a 20 log base 10 of the converter's bits, and 1.76 is the quantization noise. In many AC measurement applications, such as audio and radio circuits, noise measurement techniques are well known and typically done by analyzing the measured signal in the frequency domain. You calculate an FFT from a converter's output signal. This provides a useful estimate of the noisiness along with the key specifications. In the past, FFTs were difficult to obtain because of the available computing power. This environment made ENOB numbers very valuable. Now FFTs are much easier to generate, which reduces the importance of the ENOB specification. If you view the data in the frequency domain, you can compare the input signal energy to the energy that's spread around all of the other frequency bins. So, THD, or total harmonic distortion, is usually determined by using 7 to 9 harmonics of the converter's output data in an FFT plot. As you can see, some of the frequency bins in the FFT are harmonically related to the input of the energy of those bins. The energy of those bins determine the total harmonic distortion. THD is the square root of the sum of the squares of the harmonic components, or spurs. We usually specify THD with the input signal close to the full-scale value of the input and sampling frequency. THD is a critical specification for audio, communications, and geophysical applications. For the signal-to-noise ratio measurement, all of the energy in the remaining bins is integrated and compared to the fundamental signal level. SNR is a calculated RMS value that represents the ratio of RMS AC signal to RMS noise power, all below 1/2 of the sampling frequency. Now remember, this calculation excludes harmonic signals and DC. The ENOB trap is to exclusively use this specification when you are comparing and selecting ADCs for your application. As we know, the ENOB specification doesn't take the DC errors such as linearity, offset, and gain into consideration. Again, so the thing to remember is that ENOB is simply a figure of merit. It doesn't tell the whole story. It only remotely tells the combined noise and distortion story. Another technique you can use to find the ENOB of a converter is to measure a DC input signal. The most common measurement for oversampling converters, or del-sig A to DCs, is looking at the RMS noise. In this case, RMS is equal to 1 standard deviation of a set of data. Another term that we use to describe the del-sig's ENOB is effective resolution. This is a critical specification with wave scales or thermometers. Let's take a look at the effective resolution of a delta sigma converter. In this demonstration, we're going to look at the output noise of the ADS 1258, a 24-bit delta sigma converter. We will use a histogram to characterize the output noise of the ADC, and you will see that our histogram merely counts the number of times a code has occurred in a particular data set. If you apply a DC signal to the ADC and record a large number of samples, the result will be a distribution of codes. We will take our measurement by applying 0 volts and shorting the differential inputs of the converter together. That's why you are going to see that the center code is, and the histogram is 0. So let's look at the results. You can find the standard deviation, or ENOB, underneath the histogram. This is how the histogram helps us out. If you take the data from this histogram and calculate the data's standard deviation, the ENOB is equal to the number of converter bits minus log base 2 of the standard deviation of the data. Log base 2 conveniently converts the standard deviation into bits. With del-sig converters, ENOB, or the effective resolution, changes with changes in the oversampling or decimation ratio. In general, the effective resolution of delta sigma ADCs decreases with increasing data output rates. For this representative device that we looked at, the data output rate tracks the oversampling ratio in the converter. ENOB for AC measurements uses a SINAD calculation, which is a combination of signal-noise ratio and THD. The AC measurements is a dynamic measurement requiring a sine wave input. This is used with a converter architecture such as SAR, pipeline, flash, or a high-speed delta sigma converter. ENOB for DC measurements uses the RMS of the noise calculation. This is done with a DC input to the converter. You'll find this type of measurement is taken with slower delta sigma converters. I'm Bonnie Baker, and I'm here to tell you that ENOB is a simple figure of merit, and it has its place. But take time to look beyond Bailey's beads in your eclipse. ENOB doesn't tell you what the total performance characteristics of the converter is. In some cases, ENOB may mislead you, and you may actually have a perfectly usable converter for your application.